if we have y equals f of x versus x table, then to get the table, a table for the inverse function, we reverse the columns. We take the y column and make it into the x column we make into the y column, and then we have a table of y equals f inverse of x versus x. For example, if our table over here was y equals 10 to the x, then the inverse function would be y equals log of x. So if this is a table for 10 to the x, this would be a partial table for log of x. If y equals e to the x, then we got y equals natural log of x. If y equals x squared, then the inverse function is y equals the square root of x. And of course the inverse to the square root is the square function. When we graph these functions, the way we've reversed the coordinates, well, we have to reverse the coordinates in the graph, so that a 0y will become a 0x. And each of these points up here has its coordinates reversed. Its y coordinate becomes its x coordinate, and its x coordinate becomes its y coordinate. And if you look at how that happens, you'll see why this gives you two graphs, a graph for the function and a graph for the inverse function, that are symmetric with respect to the y equals x line. So we say they're symmetric about y equals x. And that means that the points here, each point here has a point on the opposite side of the y equals x line at an equal distance, and the line segment between those 2 points intersects this line at a right angle. And if this point is on this table, then this point is on this table. A brief review of the vertical stretching idea, which we've of course reviewed or gone over very recently, is that if we have a function f of x, then the function a f of x is going to be obtained by vertically stretching the function f of x. That means, well, if y equals f of x, then the y that we get for a f of x will be a times as big. Y is the distance of a point from the x-axis, so that means we take every point of the f of x graph and make it a times as far from the x-axis. So we stretch it by factor a. If a was less than 1, of course, it would become closer to the x-axis. If a was negative, it would go over onto the other side. But we've seen all these behaviors, and right now we're just doing a quick review. If we do an f of x plus c function, that means if we have our f of x function here, then if c is, well, c is going to be a constant number, we're going to shift that y value by c units. Now, in this case, c is implicitly a negative value because we've moved the points of the f of x function down, okay? But we're adding c. If we add a negative value, well, we're adding a negative value, and that's what we're doing here. So our f of x plus c function is vertically shifted c units from our f of x function in the y direction. This is contrasted here where each point moves a distance that depends on how far it already was from the x-axis. Here we're just moving everything the same distance. Every y changes by the same amount. Now horizontal stretch, horizontal shift. If we have a function f of x, as we've seen with tables, and again we've seen this very recently, if we replace x with x minus h, then when x is 0, f of x is going to give us f of 0. So here's f of 0. In the function f of x minus h, if we replace x by 0, we get f of negative h, not f of 0. But if we replace x by h, we do get f of 0. So when x equals h, we get the y value f of 0. So we've shifted that point, f of 0, from here to here. And we can see, if we think about it, that every other point is going to do the same thing. Whatever the coordinate, the x coordinate of this point is, if we replace x by h plus x, then we're going to get the same f of x that we had on this function. So that gives us a horizontal shift of h units.